In the previous video, we saw that PTP establishes a master-slave hierarchy. This hierarchy is actually a tree structure, with the grandmaster clock at the root of the tree and several branches that originate at that root. The leaves of the tree are ordinary clocks, and the branch points of the tree are boundary clocks. Regarding the root, it could be a boundary clock or an ordinary clock. Let's assume that it is an ordinary clock in this example. Now, clock synchronization actually only occurs directly between adjacent clocks in the hierarchy. This means that the underlying network topology used to synchronize the clocks should also have a tree structure. In this particular example, therefore, the underlying network topology should look like this. However, the topology of the physical network on which PTP is executing could actually be very different. For instance, it could be something like this. That is, a mesh topology, or a partial mesh, where several boundary clocks are interconnected. To make PTP work on top of such a physical mesh topology, there are two possible solutions. The first solution is that PTP is executed on top of a protocol that hides this physical topology and only shows a tree to PTP. This is, for instance, the case when PTP is executed on top of Ethernet and the boundary clocks are Ethernet switches that execute a spanning tree protocol. The second solution is necessary when the protocol on top of which PTP is executing does not hide the mesh topology. In that case, the boundary clocks prune the mesh topology into a tree topology by putting some of their ports into the passive state. In this way, certain links are deactivated, resulting in a tree topology as required by the master-slave hierarchy.